Yeah, so it's a pleasure for us to have Lilia here. That's Department of Physics at the University of South Florida, earned her bachelor and master's degree at South University of Maryland, and her PhD from the University of Tennessee in the US. Her work focuses on quantum materials and their ubiquitous electromagnetic phenomena for fundamental understanding of novel light-matter effects and interactions. She has published numerous papers in the forefront of condensed matter physics, as well as 2 US patents for her inventions. Three, not today. 3 patents. She was elected a fellow of the American Physical Society and the American Association for the Advancement of Science. She has also been recognized as an APS Woman Physicist 1. Is a member of the National Academy of Inventors, among others. Please take it away. It's a pleasure for us.
Thank you for the nice introduction. It's a pleasure to be here. My first time in Rio and first time in Brazil, coming from Sao Paulo. So I was invited to visit school there that also works in Casimir phenomena. I contribute in different areas in condensed matter physics, but Casimir phenomena is a direction that have been active past, I don't know, many years. And Brazil, over the years, have evolved as a place where there's many experts at particular type of science, and several of them actually sitting here in the audience. So I'm kind of intimidated a little bit. I'm going to say, I hope I don't say anything that is not correct. So yes, I come from the University of South Florida. Okay, but before I continue with my talk, I would like to tell you a little bit about the place I come from. I don't know if you were able to check it out in the web. University of South Florida is a relatively new university. It was established in 1956, but this year there is about more than 50,000 students in Rome University, most of them obviously undergraduates. And for the past several years, the university is getting better and better, at least according to some rankings that some reports are giving. So now it is number 45 public university in the US, according to this ranking. And I'm sure one reason, I guess the main reason for this is the research spending that keeps increasing every year. In 2023, more than $700 million was spent at the university. And because of all of this funding, all this money that's coming in, there is now a lot of new things, new construction and new initiatives that are happening at our university. New dorms, new health complex, market, a new bank, everything is to bring the students on campus, because after COVID, nobody wanted to come back to campus. Everybody wanted to stay at home, but now these investments are happening, and more and more students come back to campus. So there's also a new football stadium, but this is not soccer, this is American football. The newest thing is that there is going to be a new college that is going to target artificial intelligence. As far as I understand, this is the only such college in the US. That's 150 new faculty working only on artificial intelligence, machine learning, quantum artificial. Just that here, whatever that is. So this is the place that I come from. Here, that's the main road that goes into campus. And the building that I'm sitting in is right here. And the office is facing nice campus, a lot of new things are happening. So this is about the place that I'm coming from. Okay, with this, I want to now continue with my presentation. And I'm going to start with some kind of a brief introduction. And in my presentation, I try not to have a lot of technical details. I want to give you like a journey, like excursion on things that I found interesting and important in this big part of my group. So not a lot of details, but more like a progression of ideas that I've experienced personally. And the first question that I want to pose is, why Casimir phenomena? Why electromagnetic interactions? Why do we care? And it's very simple. Up to maybe several years ago, this kind of interaction was considered relatively small and important and sort of a curious thing that nature has. But what are the practical applications? What is the practicality of this phenomenon? Yes, the first, one of the biggest areas, especially in recent years, at material science, are precisely these materials that are made out of chemically inert components. Because they're not really interacting strongly with this kind of ionic or covalent bonding, you could take different types of chemically inert systems and they're held together by these kind of electromagnetic type of coupling, which is like the van der Waals force. Okay. There's also other areas where, let's say, the gecko is a picture that everybody who works in van der Waals, I mean, that's a picture. But there's also nanostructured devices and microstructured devices that always experience kind of a stiction force, adhesion that forms devices. So the stiction force, the adhesion force, is a manifestation of Casimir-like phenomena. And of course, there's other biological processes that also that are also controlled by electromagnetic fluctuation. So what is that really? How do I said the word fluctuation-induced interaction several times already. So you want to ask, so I guess the first question you ask, what is how do we really understand what is the fundamental picture that we have when we talk about these fluctuation interactions? So I want to start from two types of first principles. First principle is electromagnetic, but the other one is atomic first matter. First principle. So if I take one atom, okay, and we place it in vacuum, vacuum of course is not empty, vacuum is surrounded by electromagnetic fields. These electromagnetic fields constantly experience virtual flickering. That they keep appearing, disappearing, flickers an electromagnetic mode. Well, if the atom is sitting there, the atom is going to respond to these kind of flickering type fluctuations. And the way the atom responds is by creating these instantaneous displacement of the positive and the negative charge that make atoms. And these kind of displacements, that means that create virtual dipoles. So this is the response of the atoms to the surrounding electromagnetic. Now, if I bring another atom, this atom is going to experience just the same kind of phenomena as the first one, but now that they're close together, they're going to experience dipole interaction. So this kind of virtual dipole, they're going to now somehow interact, not somehow, but in its most simple way, the dipole interactions that we know. Okay, but if only we have one or two atoms in the universe, that's easy. That's not the case. Suppose now I have one object, okay, like this simple example here. Then I have another object that is in close vicinity of the first one. Well, this object now is not made of one or two, 5 atoms, but it's made out of many number of atoms. This object is also made of infinite number of atoms. So what we have collective phenomena. Two types of collective phenomena. One is the collective response of the atoms that make up object 1, independently of object 2, to the electromagnetic field. But then when I bring them together, now we have collective phenomena, collective type of interactions that are happening between electromagnetic type interactions that are happening between this object. So it is believed, was, most people, let's say chemistry people, they say, well, this is really not a very strong type of problem. Not that much interest. But actually, that is not the case. In Van der Waals materials, the number of physics fields will constantly be expanded to these kind of materials. Well, they're held together precisely by these type of fluctuations. Okay? And it turns out that this force is the decisive factor of the different types of stacking patterns that you may take one material and well, the stacking patterns now, they're controlled by these weak type of couplings, but at the same time, the outcome is not that weak. It's actually could be quite potential. Depending on the stacking pattern, I have inversion, I don't have. I have other, for example, depending on the stacking pattern, the electronic structure property change the composite change. For example, the famous example of sulfide, two-dimensional, three-dimensional, multi-layer composite. The Van der Waals force turns out to be the decisive factor for addition directly, indirectly. But if Van der Waals electronic structure, then somebody. So this, of course, is chemistry, and we are, as I was saying several times already, we have the Van der Waals part where the distance between the interacting objects changes like coupling happens. Although I have a lot of work in that area as well, especially on the computation side, this is not what I'm going to say. I'm going to go on to the other regime where now the interacting objects are far away from each other. And essentially, object 1 and object 2, they do not see the atomic, each other's atomic structure. So as far as the electromagnetic type of coupling between objects, they see each other as effective media. Okay, no particular position of the atoms here and here. It's not really important. So this kind of an effective medium friction allows us to write an expression for the Casimir force that I had written here in the simplest form, using the so-called Lifshitz formalism. And there are several experts this audience who work with this formalism. But the expression that I had written here relies on the reflection coefficients, Fresnel reflection coefficients that are associated with the electromagnetic boundary conditions. So I'm not going to go into details how this is derived, where it comes from. Rather, I'm going to use this and now look and see how this force is being modified with the IC. So there are two things, okay, looking at this expression, two things that I noticed immediately. One is the role of materials, which is captured into the dielectric and magnetic response, which obviously enter into the reflection coefficients, right, for Maxwell's equation. But in the reflection coefficients, there's also the role of geometry. right? So depending on what material and what kind of geometry it is, these reflection coefficients. So in my work, I had focused on the type of materials that enter here rather than on the geometry. Everything that I'm going to tell you is about planar objects, where this expression will work. So because of the interplay, unintuitive interplay between geometry types of the outcome of this expression is not really, we can't really say what it is. It's very unintuitive. So this is a universal force, but it has a non-universal dependence on fundamental constants, on the scaling law, sign, the magnitude. So we know how to, I guess, express the interaction, but we don't know what the outcome is. So this is not like the Coulomb force, where I know that the scaling law is also one of the squared. Two charges kind of thing. Not the case here. So in fact, depending on what the material is, outcome is the same. This is what I started after several years ago. So as advertised, what I want to look at is what the Casimir interaction looks now, can be changed, can be modified based on different types of materials. And the first type of systems that I want to introduce to you are 2D materials that have non-trivial topology, band topology, such as rack materials and churn insulators. And as an example to this type of system, I'm taking a graphene, the graphene family of materials, graphene, silicene, germany, stannine. So all elements in the carbon group, they have this kind of hexagonal form, and graphene is flat, but silicon and all others are not. One family. And it turns out that there are not only 2D topological non-trivial materials, but there is also 3D. As for an example, for another example, to explore Casimir phenomena, looking at Dirac materials, a specific type of Dirac materials, such as vowel semimetals, and here's one example. So there are many types of vowel semimetals, but I've just given one typical chemical composition. But there's also quasi-one-D systems, right? Such as if I take, for example, the graphene, and if I cut the graphene in a certain direction, I can make a ribbon. Depending how I cut the graphene, I could have an armchair or a zigzag ribbon. But I could also have carbon nanotubes. That's another quasi-one-dimensional system that now, depending how it's wrong, properties of carbon nanotubes. But there's also metasurfaces now. This is a new emerging object that people are studying, especially for optical applications, okay? Such as carbon nanotube fumes that are made out of single wall, parallel carbon nanotubes that are equally spaced. They're placed in the back, right? So these types of very thin metasurfaces have great application for osmonics and photonic applications. So I want to study them in the context of Casimir phenomenon as well. And also piezoelectric material. Piezoelectrics are new for the Casimir community. I would say these are new types of systems, because now not only are we talking about electromagnetic excitation, but phonons, because piezoelectrics, coupling between the electromagnetic and the phonon is going to modify optical and electric responses to So the material that is a poster child of piezoelectrics is silicon carbide. So there are groups that are studying silicon carbide the only thing that's being studied, right? For years, and we still don't know everything about silicon carbide. The first thing that I learned is that depending how cut the surface of the silicon carbide cut, there are different polytypes. Each polytype has its own specific piezoelectric property. Quite interesting and unusual. How does that affect Casimir? So, before I continue with some results for Casimir phenomena, I want to stress that the dielectric response is of utmost importance. If I don't know what it is, if I don't have a good understanding, I don't capture all, I guess, phenomena that determine the dielectric response, then my study of Casimir phenomena. So, from all the regimes that let's say the dielectric response exists for wide frequency regime, Casimir phenomenon at the low frequency regime is utmost important. This, by the way, is the regime that is most difficult to assess experimentally. So, but nevertheless, on the theory side, because now I'm mostly focused on the low frequency regime, that gives me, Casimir phenomenon gives me tools to probe effective models of the electronic structure of the materials themselves. And then these effective models then are used in linear response theory, like the Kubel formula, to obtain the dielectric response as well. If that is not enough, then we have to go beyond that and employ first principle simulations, at least at the rate of get meaning of the dielectric person. So with this, I want to say, pause and say, well, Casimir phenomenon now, I want to study this area of physics. They motivate study the basic properties of the material. If I'm able to report what the dielectric response is, now not only am I helping the Casimir community, but I'm much more. Once we know the dielectric function of the material, then we know so that's another motivation. So I want to start with the 2D Dirac physics in the graphene family. And it turns out that we can write an effective Hamiltonian for the low energy physics of this kind of system. And graphene is flat, but silicon and everybody else in the periodic table are not flat, they're staggered. So it turns out that because of the staggering, if I apply an electric field perpendicular sheet of the two-dimensional, the 2D layer, and I also apply a laser, right? We can control what the magnitude of this energy gap is going to be. Okay, and as you see, so this energy gap now has two indices. One is a sublattice index, one is the spin index. Okay, and you have several parameters. We have the spin-orbit coupling, which for graphene is almost non-existent, but for the other materials it can grow substantially. There is the staggering parameter that allows us to have this kind of part in the gap, and of course there is the laser parameter that is a composite parameter of the intensity and the frequency of the laser. So the non-trivial topology of the material is controlled precisely by this energy gap, which now gives rise to the Chern number. Depending on what the Chern number is, we get an array of topologically non-trivial phases of this family, which I have written here. We have something like anomalous quantum Hall effect. I don't know, spin polarized metal, single Dirac cone, polarized spin quantum Hall insulator. And these are simply controlled by how many gaps are being opened and what is the magnitude. Everything controlled at this chart now. So I just want to point out that this Venn diagram, this phase diagram, by the way, is unique to this 2D material. Some of these phases, they cannot exist in any other system, only for this family. Now, if I take this phase diagram, now this phase diagram translates into phase diagram that interaction experience. Because obviously, each phase, the optical response or the electric response. And here is the phase diagram of the quasi interaction that I have given. Many interesting things that are happening. Diagram. I would say that the most curious one is when the two interacting materials are in the quantum anomalous Hall effect, where the interaction energy is proportional to the product of the two Chern numbers. Because the Chern numbers now could be positive and negative, product could be positive and negative, and it could give rise to. That's interesting. The other interesting, kind of discouraging, is that you see the interaction between two graphene layers in the asymptotic pattern is proportional to fine structure constant, alpha. And it's metallic, right? Proportional to now. So the two graphenes interact in proportion to fine structure constant, but the two materials, if they're in the quantum anomalous Hall effect phase, they're evenly, because the interaction is proportional. This is kind of discouraging because something is proportional to a very small number. One idea was put forward, the number 100,000. There are no limits of how big the Chern number is going to be, but it's very unrealistic. So it's an interesting result, but not really easy to observe. Nevertheless, the Casimir interaction, the motivation, prompted us, motivated us to understand the electronic structure and how about 3 dimensions? Okay, so I said, okay, well, maybe the reason why we have this alpha squared is because of the dimensionality. If I go to 3 dimensions, maybe the result non-trivial topology is going to have a bigger result. So again, for a 3-dimensional vial semi-metal, we can write an effective Hamiltonian that I had given here. And it turns out that this Hamiltonian looks a little bit more complicated, but it's still simple. Looks simple. We can find the eigenstates and eigenenergies. Here is the eigenenergy that I have written here. And just to say a few words about what a vial semi-metal is, well, the vial semi-metal is also characterized by Dirac linear band dispersion at 2 cones. But unlike the case of the graphene, where the 2 cones are degenerate, in the vial semi-metal, which now has to be mostly a 3-dimensional material, the cones are separated, so they're non-degenerate. And this non-degeneracy is lifted, so I'll say here in a minute what it is. So I try to put it here schematically. So that's one difference. The other difference is that not only now the cones are separated between each other, they're separated by this B parameter that here. But now the cones could also be tilted. Depending how much they are tilted, we have a type 1 and a type 2 calcium. So already things become complicated. So this B parameter is a topologically non-trivial property that we focus on. Well, now if the displacement of the cones is in space, right here. Have an additional non-trivial property comes from Fermi arcs on the surface. But if the displacement of the cones is in energy space, nothing like that. Okay, this is controlled by a time reversal symmetry that is being broken or an inversion symmetry that is being broken. Now, if the cones are now tilted too much, there is also another thing that, which is the density of space of the electrons and holes now is significant. So this Hamiltonian, by the way, looks simple, but that if we want to obtain now the electric response based on the typical linear Hubble response formula, linear response Hubble formula, we are not able to write a succinct expression. Expression is quite long. Here. And so all this agony and all these technical details, we go and compute the energy, Casimir energy. Here it's normalized to the 1 to 2% metals. And as you can see, nothing is actually the 2 valence metals behave like dirty metal. As you can see, no matter which parameter change, the type of the material, the Fermi velocity in terms of characteristic behavior. So it turns out that not only is the topology small, the effect of the non-trivial topology is small, but it's now masked, it's covered by the typical electric response. A lot of technical work, but the payout in terms of Casimir non-trivial effects. One thing, however, that we noticed is that our results depend on a particular parameter, cutoff energy, that must be present in the model. The cutoff energy is the size, how big the linear dispersion of the Dirac cones is going to be. So, back. This is this parameter, which here, as you can see, so the energy window that I have to assume for the validity of the linear response now enters my model. Okay, and there's no way going around it. Well, if that is the case, as a person from the method of the signal that my effective model model that is may not be for this time. Okay, then I said, okay, so there's seems to be something curious between Dirac physics and geometry. And I asked the question, why don't I just take a step back and just focus on the type of dispersion that Dirac materials have compared to the typical parabolic band dispersion that typical materials have, and now study the role of geometry. So what I said, I'm going to look at quasi-1D materials separated by a distance, two-dimensional materials separated by a distance, three-dimensional materials separated by a distance. And in each case, I'm going to say that the material that makes up the 1D, 2D, 3D material is going to have this form, that form. So again, a little bit technically difficult, but what we find is that no matter what I do, what kind of dispersion we get, as long as we're talking about 1D or the 2D material, all the temperature is the same. In other words, by now I'm not looking exactly at the quantum regime at temperature 0, but I turn on the temperature. Everything after 30 Kelvin is masked by the classical thermal fluctuations that And this is, I guess my pictures don't have very good resolution, and this is true for 1D Dirac material, 1D standard material, 2D Dirac material, 2D standard. Doesn't matter. So for phenomena, if I'm looking at a regular temperature, the topology type of material doesn't matter. All it matters is the we want to really observe some kind of quantum mechanical image. Doesn't matter what the temperature overtakes everything. Very unusual and some kind of maybe not very simple. So, in addition to dimensionality, now we have also anisotropy. Now, anisotropy has two types. We have two types of anisotropy that matter to us. One is the geometrical anisotropy, and the other is the optical anisotropy. And these two are related together. So, if the material is anisotropic, we also have not only the energy of Casimir interaction, we also have Casimir torque on relative orientation of the optical axis. So my thought process was, if I look at now not one dimension, not one carbon nanotube, if I make a metasurface like here, so I have many parallel single nanotube placements at the substrate. This is the process of a isotropic. Maybe it's kind of two-dimensional, or that's not exactly two-dimensional, but this ultra thin film can, even better to observe experimentally. So this is what I said. Well, I'm going to look at these ultra thin parallel single or carbon nanotubes each in substrate, and the first thing I want to do is determine what the dielectric. Turns out that the dielectric response is extremely complicated. One whole phenomenon that governs at the surface. One thing is that there is the role of plasma. I mean, first of all, obviously, the type of carbon nanotube and periodic is going to matter. So I have to know how to compute, how to calculate the dielectric response of different types of periodic nanotube. The second thing, there is a strong plasma effect that is especially pronounced for intra or larger dielectrics in the band type. Then there is also now another that comes from the intertube factor that creates a new type of plasmonic mode. This plasmonic mode is non-local, and it is due to this intertube force interaction between the tubes. So very complicated, very cumbersome, and yet somehow we managed to come with some kind of a succinct expression that I. So then what we look at, again, with the Lipschitz formula, we can calculate the interaction and also the torque. And here I'm giving you the quantum limit of the energy and the torque. And here I'm giving you the interaction energy for two different temperatures for the same type of surface. So I'm going to start in this case. Quasi-2D system, temperature as you can see. At 300 K, almost everything is red. In other words, the thermal fluctuations, classical thermal fluctuations, overtake the entire Casimir interaction. If I go at the quantum limit, which is at 0 temperature, we see these characteristic behaviors of periodicity, of the dependence of the energy function of relative forces, and that helps us to compute the well, which is also an expected thing. One thing, however, that I noticed, and I didn't realize that before, that now energy, the Casimir energy report sort of experience this kind of a curious separation of the thermal effect. So for the interaction, the thermal effect dominates. And it always takes energy for temperatures that are 30 Kelvin and above. Larger distance. But it turns out that the zero metabar for the torque is zero. Actually, all a number of particles, the torque is really small. So the torque, because it's determined by the anisotropy, dictated by the large itself, while the energy by the small. So what that says is that the energy is determined mostly by the torque. And I thought maybe because this was the anisotropy of the material is huge, and it's going to yield very large numbers of torque compared to what's observed experimentally. It turns out that actually it is rather small. To observe experimentally. And reason for that is precisely this. Yeah. Somehow the non-locality kills the magnitude of torque and also. So another green scratch. Yep.
Special about delta equals NR?
No, just one example. We couldn't go too close, let's say, because then maybe the physics is the response. Separation. Oh. Quantum mechanical particle charge. Yeah, the magnet is small. I don't remember the numbers. But so I can compare it with and the reason, again, it's all because of the non-locality and the finite thickness of the field. That is not intuitive. Okay, so we continue. I want to continue my journey and now take you to piezoelectrics. Okay, well, piezoelectrics now are another set of materials that help us understand Casimir interaction, but from a different perspective. What is so special about piezoelectric systems? Well, as you know, they are polar materials, but a subset of the polar materials, piezoelectrics, is the main feature is that when the acoustic wave that impinges on the surface inside the field, it creates a decaying evanescent field. So this acoustic wave, obviously, it has a form of origin. If I bring the two piezoelectrics together, then that gives me a chance to study Casimir phenomena affected by which I have written here. Well, again, what do I need to know? I need to really now understand not only the electric response of the form, so I need to know the phonon degrees of freedom in the piezoelectric material and how they couple with the electromagnetic field. Then, obviously, I need to modify the electric response, and we need to modify the boundary. As you know, this displacement vector, which has the typical field, but also the acoustic or the phonon displacement. So we looked at this problem. And we considered a system that is made out of semi-infinite substrates. One case, another case is two substrates are covered by two graphene. Then we looked at the case when the substrates have finite thickness, so the substrates with finite thickness LZ, and the fourth case is when they could be covered with a graphene sheet like that. And the physics is complicated, also the mathematics is not that easy. We arrived at a revised reflection coefficient, which I had written here. And these reflection coefficients include an extra term only in the PP mode, not in the SS mode, so this particular mode. And this extra term gives us now the coupling between the optical phonons that are responsible for the piezoelectric effects in these Q values and the electric functions of the real. So not easy, and it turns out that despite the fact that piezoelectricity has been around for a long time and many people have studied it, somehow nobody has derived out of the simple working expressions for reflection coefficients. So the first thing we looked at is the type of modes that appear in piezoelectric. So there are phonon polarity modes, which you can determine from the reflection coefficients, the reflection coefficients in the real and the imaginary domain. But there's also surface phonon polarity that are specifically from the fact that there is a surface reflecting. And we also discovered a new type of phonon. Okay? And this new type of phonon is a peculiar one. It has a mixed longitudinal and transverse polarization. And this new type of phonon polarity is only present in specific polytypes. It does not exist for all types of only types of polytypes, so there's a peculiar, form. We'll get some details. And by the way, this new type of phonon polariton, we call it longitudinal transfer surface phonon polariton. And it is, you can see it here, these flat lines here and here. The peculiar thing about this phonon polariton is that it is accessible to very large. By the way, there's already some evidence. Again, look at Casimir, then after understanding the material, and if I'm now a semi-infinite substrates, like the one I have drawn here, and we cover them in graphene or not, look at the interaction. And we have now not only the thermal wavelength, we have the graphene characteristic wavelength, but there's also two other wavelengths that are associated with the longitudinal and transversal. Nevertheless, all this complexity, we see not a lot of, not really anything interesting, right? Comes to the so at small distances and large distances, there is some kind of a transition, but doesn't really matter what kind of baritone surface. Role has a magnetic effect if the substrates are semi-infinite. However, the substrates now finite, okay, what we see that in the case when we have these kind of special types of new types of longitudinal transverse surface phonon polaritons, there are resonant modes. And these resonant modes are controlled by some kind of, trigonometric function that now is controlled precisely of the wave vector of this longitudinal. Well, so depending on how thick my substrate is, we get an interaction that is in a positive magnitude, and we can experience some kind of 1 over d to the 4th, 1 over d to the 3rd. But in any case, resonance, because of this this is a way to modify Casimir interaction in a very the search is something that is and then I want to end with the stars that shown in physics, which are twisted bilayer graphene. All about this kind of system are twisted bilayer graphenes at magic angles. Moray pattern materials now are very on the metaphysics. The simplest one is the twisted bilayer graphene at a magic angle, which is about 1 degree. Oh, I have one graphene sheet and another one, and I just hold it. One the other by 1 degree. Then we have a material that can be logical physics. I don't know, the map space. All sorts of topological. These are accessible, very small, minute changes that the further position can give us. So by changing the substrate or changing the temperature a little bit, these are all experimental. Nothing coming from you, experimental. We get an array of different things. You get this all at this particular angle, only at this 1 degree magic angle. Why nobody knows? Why is it also called matter? One thing is known, however, is that all of this is due to the strong effect of high correlation effects that are happening in high correlation effects. High flat band, but only for this particular. So, correlation effects are very difficult to model analytically, say, by graph, 3D or even the carbon nanotubes. Very difficult. It's not easy to do that. It's not easy to do that from first principles. If I want to model the material, if I want to compute it from a SD function theory, I need to create unit cell that is over 11,000 hours. Don't have to. How? Even if you do, then the calculation will have. Well, so what do we do? So we step back and look. Okay, so we see that at this 1 degree offset, what I have is that I have these moire patterns. Okay, I have a region that has this kind of AA stacking, which you see this one right here. But then I also have another region that has an AB stack. Stackings that are nobody knows about graphing. So the repeating, of the AA and B stackings, so it looks like a class. And the length of the lattice is order of the micrometer. Very large. Very big. But the length of the lattice of the graphing sheet itself, whatever number. A lattice constant graphing. However, so we rely on yeah, that seems to be working. That's my dog. They say, well, I can mimic what is happening in the laboratory by modeling kind of red color system by a small set of high-value functions, and in this particular case, we have 10 of those. And each one, so depending on the symmetry of the material, the symmetry of the red color, these types of the number of bands and the types of bands on graphene, it has some kind of I don't know, P bands. It has a PZ band, but it has high binding functions. And each one of these types of high binding functions has a parameter. Each one of these parameters is going to control a particular type of symmetry that is controlled. If we follow Professor McDonald's idea that, well, because of the competing effect in strong correlation that occurs, these competing effects don't symmetry that are being broken simultaneously. I change my substrate, or maybe I change the free level by putting a little bit of field open. Every time I tilt somehow one of the symmetries, I cannot model this principle in reverse, but I can mimic what happens in the lab by introducing these parameters. This is what we've done. So again, I don't want to show you details. And this is my system again. I have a system phenomena, and I'm taking the simplest case when none of the symmetries are broken at that match table. And what I see is that the asymptotic behavior, in other words, all my parameters are zero. I have these 10 bands, tight binding functions, but all of these parameters, none of the symmetries are broken. So asymptotically, what we get is that the interaction is twice the interaction of variable. Two times graphene layers. And then the most interesting case is when this the time reversal symmetry is broken, okay, which we can control via some parameters here. And we covered this case when the time symmetry is broken. Bilayer graphene, magic graphene, bilayer graphene is okay. And we covered specifically that the reaction now is proportional to the fine structure constant square times the product of the two Chern numbers. So if the two Chern numbers are positive or negative, the interaction is positive or attractive, as you can see here. And when the C2 symmetry is broken, then we don't get that effect. So, and now, yep, the next version. Yeah. Yes. Definitely. Talk about here. Yeah, that's the same expression for channels and cover for the 10 band of bilayer when the bilayer so we recover the asymptotic expression. Confidence that, you know. And then when the C3 symmetry is broken, which is automatic phase, and we get essentially the dirty metal. You see it in here, and we can achieve this via different parameters. So this is an automatic phase, by the way. the only one that is also has finite graphene is in a lemmatic phase, and the there is another one. So with this, my journey ends. I'm going to start end up start the show, and I hope I was able to show you that Casimir interactions are a fundamental that helps us, that is probes. I understand only max but it also motivates people like me from the condensed matter perspective to study material. Yeah. I don't understand the electronic structure first and foremost. Then the bond, the phenomena on the aspect are not going to model properly, and I will also correct. In this kind of niche area, I would say, so it's considered to be niche area, but as you've seen, it requires many other areas. No. Okay, so it touches many other areas, for example. It motivates us to make sure that our analytical models are good enough. Then, if that's not enough, then we have to go to numerical better model basic. So with this, I want to be done. Thanks for that. Casimir phenomena are really worth studying from different.
Population.
Yeah. Yes. Yes.
Okay, and then with non-locality, they apply, and then the non-locality.
So this non-locality appears because the thickness of the tube of the film not zero. It has a finite thickness. So it is not a strictly 2D material, but it's ultra thin, it's quasi 2D. And that thickness, finite thickness, which essentially the diameter of the nanotube will even more if the substrate is bigger, forces us to consider that I have now a distance-dependent Coulomb interaction associated with the dimension of the field. And that presents some kind of complications, okay? And it introduces non-locality. So it introduces a wave vector in that plasma simply because it has finite thickness. And that's also related so theories in the paper is also related to how distance between the two. So the response of the medium, like medium response, but the exact electronic structure, the chirality of the nanotube is exact. There is already a tool to do this. So there is a tight binding model that we have developed. Actually, other people have also, where you can, depending on the chirality of the tube, calculate optical response of the individual nanotube. The thing about the carbon nanotube is that turns out that for both single but also to double, I guess. Carbon nanotubes, there's an exciton effect that is quite strong. Excitonic plasma exciton coupling in the tube itself moves displacement because of the strong coupling could be quite. But for Casimir, it turns out that exciton plasma is not that important because all we care is what happens at interband types of. They make a small event. What really kills the interaction? Actually, the interaction is quite reduced because of the finite digits of this non-metallic. Kills the interaction.
You get more. This
Possible. You have all conditions, and the boundary conditions fewer reality and important. What not easy to say. So I had a lot of criticism last event, I think during the presentation. Who is not really not the case. Coming in all angles. Couldn't say that right. I'll tell you one idea that was perfect. Casimir volleyball. We're looking at form. The only material types of systems that I know, not before I read. So when I looked at the literature, there are very complicated papers that people but nobody really gives us some kind of working people want that's reliable, the coupling fully that's we went to the but that's the only one that I know. Right, so I now want to look at follow on the option where let's say you have two systems serves as a transfer. Transfers or chemical. Looking this is probably organizations as anything all part of the factors. Recommend only 5 meters. Read out. Turns out it's sunny, right? So it doesn't. Here we have nothing to develop. Papers that have been published in
This this demo.
Say that again?
Is this demo or is next demo right?
No.
I mean, it's small. They are just demo form, but they are driven by.
Oh, they're not driven. It's just the material is that.
So it's really demo.
That's
Still we find this normal.
yeah, only for finite thickness materials, and only for if there is this particular mode, the longitudinal surface form polarity mode, only for that one.
But we're analyzing just the people.
No, we're analyzing.
The total force.
Well, let's see where we go.
Because there was a good
Yeah. So so in some kind of asymptotic limit in the T equals 0, but also in the large temperature machine, we have this 1 over d to the 4, 1 over d to the q, which is characteristic behavior. But there's also a factor here, and this factor depends on the piezoelectric coupling.
Okay, but it doesn't depend on this.
It does not.
Oh, okay.
But yeah, so there are, and by the way, this is not, you know, it has some kind of peculiar resonant conditions that this new mode gives with the distance of the thickness. I mean, with the thickness of the individual layer. So there's no
monotonic.
Yeah, it's monotonic with distance. Yes. So the way I understand it, we have the finite thickness plane and another one. And in the boundary conditions, I have this reflection from one boundary, but also from another. But then also have similar reflections inside the gap. Well, if the substrate is semi-infinite, this kind of, you know, constant reflections, you know, and transmissions inside the material, they're missing. But for the finite plate, you know, they create this kind of, you know, this don't way to describe it, like a resonant-like type of action. This does not depend on distance. Only depends on the size of the plate, and this is like a wave vector for the longitudinal optical.
There's the thickness. State that topic as well. And so the company, electric strain, possible to get us each does it depend strongly
Yeah.
The first formula, just EI, it has a strong dependency with frequency.
So this in the general form, epsilon is 10. This is also, but in my case, I'm taking the most case. So this E doesn't depend.
Okay.
But it's a very complicated thing. The first thing I was trying to say, okay, I'm going to take the most general. I look and see what the most general, what is how this kind of nanotrial. Somebody has worked and determined what these you know, these tensions are. So contracted. I gave up. And even the paper that they just list them, but they just like
Third order, that's correct.
so this is quite complicated. But also some metric, let's say, make it bigger in one direction. Can we make it? Have to keep all terms. So we went back many years ago and found this green one of one. Oh, and even for that model that used to work well, carbide, nobody had bothered to translate it. Right. And in the polymer materials, have an effect of the piezoelectricity, but this effect is in the opposite of the sun. So if you see a more your heat to reflect. Well, piezoelectric, you have that, but you also have this thing here. Oh, as long as you have this, then your boundary. I mean, closing them. At 45 boundary condition, but it first fresh. Very. Well, send me an email. Or if you're interested in do PhD, come over.